Let's go ahead and talk about the lab. So we're just going to talk about the pre-lab questions. So I think you hopefully remember from class how I told you to write up the rest of it, or for now at least. We didn't talk about that much of it yet. But in the pre-lab, there's some tricky stuff in here, so I want to make sure that we go through this and it makes sense to you. Number one, I think you can handle. What measuring devices obtain precise measurements of volume, which ones obtain approximate. I think you can take care of that one. It starts to get a little bit harder here on number two, right? A balanced half reaction for the reduction of permanganate ions in acidic solution. What are the oxidation states of manganese in this reaction? Okay, so that probably doesn't make a lot of sense. You might not even know what permanganate is necessarily. So let's go down to the explanation to strengthen student understanding here. So it talks here about potassium permanganate, which is KMnO4. So the MnO4, the permanganate part, is MnO4 minus, right here. Okay, so that's permanganate. And then it's saying you need to write the balanced half reaction for the reduction of permanganate. Well, they kind of help you out with that too. I don't think that the AP exam, definitely not on my test, I don't think they would expect you to just know this off the top of your head, what would happen here. But when permanganate, now you'll know it because we're talking about it in the lab. When permanganate reduces, it gets reduced down to Mn2+, okay? So that's going to be your first balanced half reaction is MnO4 minus going to Mn2+, okay? So they want you to write the balanced half reaction for that. So at that point, now you're just doing everything that we did in class today, because they're saying you're balancing this in acidic solution. That's code for you can use H+ and you can use H2O to balance, all right? So then you'll just balance that first half reaction that way, okay? I think you guys can figure out that part on your own, but I just needed to get you kick-started on that. The second part here is there's a lot of pre-lab here. The balanced half reaction for the oxidation of hydrogen peroxide. Okay, so hydrogen peroxide is H2O2. Okay. What happens when hydrogen peroxide breaks down is it changes into H2O and O2. I don't know if you remember that from last year, but we talked about that last year. We might have talked about it this year a little bit too. I don't know. Anyway, the reason that that's called an oxidation is because over here, the oxidation state of the oxygen is a -1. Over on this side, well, actually it's a 0 and a -2. It kind of, the oxygen gets oxidized and, wait a second. Oh, that's right. Okay, I guess, yeah, when we add them together, this is gonna fix itself. You gotta write the balanced equation for that too. There we go. Okay. So the oxidation of hydrogen peroxide. Okay, so maybe they're just wanting you to write the one, yeah, that's probably what it is. This is going to be the balanced. I just kind of did the whole thing all at once. If you were just writing the oxidation part, then you would write H2O2 going to O2, right? Because the oxidation, it's losing electrons, so it's becoming more positive at that point, so it goes from a -1 to a 0, okay? But then, yeah, see, I jumped ahead of myself here. Let me back up. So H2O2, the oxidation of H2O2 would be where it changes to O2, right? But then to balance that thing as a redox, you would just add in the water to balance the, I guess you'd end up adding H+, wouldn't you? Now I'm confusing myself. And this is on video. It's always fun. Should work these things out ahead of time. Okay, tell you what, I'm going to pause this for a second. I want to make sure I'm explaining this right. Okay, sorry about that. So forget this. I apologize. That's the overall reaction when hydrogen peroxide decomposes, but that's not what we're talking about here. We're talking about just we're focusing on the oxidation part. So you're going to write it like this, and then to balance out your hydrogens, you'll do what you would normally do here. This is an acidic solution, so you're going to put 2 H pluses over on this side, and then balance your electrons from there, okay? So that's your second half reaction there. So then the balanced reaction for the reduction of permanganate by hydrogen peroxide. In other words, the permanganate's getting reduced and the peroxide, hydrogen peroxide, is being oxidized. So then you just basically add those two together, okay? So then you're going to, again, you're just going to do exactly what we did in class today. You'll have to make sure that the number of electrons from one half reaction and the number of electrons from the other half reaction are equal to one another by multiplying if you need to, and then you'll add those together. Is that making sense, or do I need to go through the whole thing here? What do you think? Because I just made that really confusing. Here, let me show you real quick. So you've got your MnO4 minus, right? And that's changing to Mn2 plus. We know that. And then we've got the H2O2 changing to O2, and then, you'd have to balance both of these, okay? And then you'd add them up after you balance them separately, okay? That's what number 4 is asking for. So 2 and 3 are just steps in the process to get to number 4, all right? Number 5, write a balanced half reaction for the oxidation of iron 2 ions, okay? So iron 2 is another way of saying Fe2 plus. The Roman numeral tells you the charge, right? If that's going to get oxidized, what's the charge going to change to? Right, it's going to have to be a bigger charge, right? Now, maybe you know this about iron, maybe you don't. They would probably be a good thing to know some of the typical charges on some of these transition metals. Fe2 plus, it can only go to Fe3 plus. That's typically your highest charge that you would get on an iron atom. All right, so that's the only possibility if it's being oxidized, is for it to become a 3 plus instead of a 2 plus. Balanced half reaction for the reduction of permanganate by iron 2 ions. Okay, so basically what you're doing on number 6 is another one like number 4, okay, where you are, you're basically adding this half reaction, which we already wrote up here, to this half reaction, okay, down here. And then they're also asking how many electrons are transferred in this reaction. They're asking that for both of those. So maybe I should just work one of these out. Feeling like that could be helpful. So looking at this first one here, I got to do this fairly quickly, but so on the first one, we've got 4 oxygens on the left side, so we need to add 4 water molecules over to the right side. Now we've got 8 hydrogens on the right, so we have to add 8 H pluses over to this side. That gives us a total 7 plus charge on the left and a 2 plus charge on the right, so we need 5 electrons to balance out the charge. On the second reaction here, we need to put 2 H pluses on the product side to balance out our hydrogens. Our oxygens are already balanced. Now to balance the charge, we have to put 2 electrons over on this side, okay? So then what we're going to have to do, in this bottom one, we're going to have to multiply by 5, and in the top one, we're going to have to multiply by 2, so that we are gaining 10 electrons in the reduction, and we're losing 10 in the oxidation, okay? So then the answer to how many electrons are transferred is 10. Okay, so then you would add that together, and that would give you the total. All right, so then you're going to do the exact same thing on number 6, except instead of using the H2O2 going to O2 reaction for the oxidation, you're using the Fe2 plus to Fe3 plus for the oxidation. Number 7, besides iron 2 ions and hydrogen peroxide, what are 1 or 2 other species that could be used to reduce permanganate ions? Okay, any ideas there for examples of something we could use besides iron 2 or hydrogen peroxide? It doesn't have to be a 2+ charge as long as it has the capacity of giving away more electrons, right? In oxidation. So I mean, think about any transition metal that has a lower charge and a higher charge. Pick the lower of the two charges, right? And that species could reduce the permanganate. Does that make sense? Yeah, so copper 1, right? So copper or I don't know, chromium 2, you know, you've got chromium 2, chromium 3. Yeah, anything like that that could be oxidized. Or, I mean, you could even pick something like sodium. Okay, that would be kind of an intense reaction. But you could pick sodium because sodium can be oxidized. It can lose 1 electron, right? So anything that can be oxidized, you could use, right? Because the permanganate is the one that's getting reduced. Okay. All right. So then you've got number 8 here. Sample of oxalic acid was analyzed using a standard solution of KMnO4. 25 milliliters is titrated after heating. 12.30 milliliters was added to the sample when a faint pink color was observed. The balanced equation for the reaction is shown below. Okay, so here's your balanced equation for this one. They're nice enough to actually give it to you this time. They're asking, what is the ratio of MnO4 minus ions to H2C2O4 molecules in the reaction? I think we can probably answer that one, can't we? That's the kind of question you want on the AP exam right there. It's going to be a 2 to 5, right? Let's look at the coefficients in front. How many moles of MnO4 minus ions reacted with the given amount of oxalic acid solution? Okay, so now we've got to figure out how much oxalic acid that we had. So basically we did a titration here, right? So this is going to tell us right here how many moles reacted with the oxalic acid. Okay, so you've got a molarity, you've got a volume, multiply those two things together, that will give you the number of moles, right? So then the question on C, how many moles of H2C2O4 were present? What's the answer there? And you have to be a little bit careful here, right? Because this isn't, everything we've done with acid-base titration so far, it's pretty much been a 1-to-1 stoichiometry. That's not necessarily the case anymore, which is actually why they asked you question A, to get you thinking a little bit, okay? So if we want to figure out how many moles of H2C2O4 were present, basically we need to figure out if we have this many moles of the permanganate, then how many moles of this must we have had for it all to completely react? Does that make sense? Okay, so you can assume if we're titrating to the faint pink color, then you can assume that's when the reaction has completely... And see, that... Did they talk about that up here? I think they may talk about that up here in the background information. Or the... well, actually, it's afterwards, isn't it? Let's see here. Okay, here we go. Deep purple in solution, the Mn and KMnO4 undergoes reduction very easily. In acidic solution, permanganate ions from KMnO4, reduced to nearly colorless Mn2+. Okay, so we've got, does it describe it being purple to begin with? Now, where am I? Well, yeah, that's not super clear. But basically, when you get that faint pink, what that means is that, yeah, basically the reaction has has completely gone the other direction. Okay, so now now it's been completely changed into the Mn2+. Okay. Okay, no, wait. It's going to get, I'm saying that the wrong way. It's going to get faint pink first, right? If you start to add any more of this after this is all reacted, then it's going to start to change more of a purple-ish color, okay? Because then you're just adding excess of the MnO4 minus into the solution. Does that make sense? So that's not, I mean, they did not make that very clear. Unless I'm missing it somewhere else in the lab, but at least I'm able to kind of tell you this. Okay, anyway. What was the molarity of the oxalic acid solution? So after you figure out how many moles of that were present, then you've got moles of the oxalic acid, you've got the original volume of the oxalic acid, so you should be able to figure out your molarity at that point. If the density of the solution was 1 gram per milliliter, what is the percentage by mass of oxalic acid in the solution? I wonder why they're asking you this question. And it probably has something to do with the fact that you're eventually going to use this exact calculation to figure out the percentage by mass of hydrogen peroxide in your solution, right? So that's why they're asking you this. So what we know right now, we just figured out the molarity of the oxalic acid, right? That's moles per liter. Oops, sorry. Not molarity per liter, moles per liter. Okay. And we know the density of the solution is 1 gram per milliliter. Okay. So, so once you know the molarity, now I'm a little bit stuck. Let me pause it for a second because I don't want to keep wasting video time. Okay, sorry. Outthinking myself here. This is not all that difficult. So what they're telling us here is the density of this solution is 1 gram per milliliter. Okay? You can use that in conjunction with the 25 milliliters of the solution that we have. Yeah, that is a period up there. Okay, I have to make sure that I was reading that right. So basically, that's telling you there is 25.0 grams of our solution. Okay. Now, in part C, we figured out how many moles of H2C2O4 were present. So however many moles that is, you just do a little stoichiometry here, dimensional analysis, I guess, to go from moles to grams, and you're going to have to figure out the molar mass of the C2H2. I wrote that in opposite order. But H2C2O4, you figure out the molar mass up here, okay? And then that's going to give you the number of grams of C2H2O4 that you have, okay? So that would go on the top here, whatever that is, and then you multiply that by 100, okay? Because what we have is an oxalic acid solution. That's, when we say solution, basically that means the oxalic acid is dissolved in water, okay? So for finding a percent by mass, you take the percentage of whatever's dissolved in the water divided by the total mass of the solution times 100, okay? So that should give it to you there once you calculate that. What does the faint pink color indicate about the reaction? That does indicate the end point of the titration, or the equivalence point. It's faint pink for a different reason than you're used to this being faint pink, right? Because usually we put phenolphthalein in these and they turn faint pink because it's becoming more basic. Here, that's not the reason it's faint pink. The reason it's faint pink, and I think I said this already on the video, is because your MnO4 has reacted with the H2C2O4 and it's changed to Mn2+, okay? So that's going to give you a faint pink color. Now, if you add any more of the MnO4 after that point, now that becomes your excess reactant, and you're going to start to get a purple color instead. Okay? But that faint pink is going to tell you that we are basically to that endpoint because now we have added just as much MnO4 minus as there is H2C2O4 in that solution. And if you add any more, then we're at the point where it's starting to go from a pink to a purple because of the MnO4 minus. All right? Okay, Prelab Part 2. Access the following animation to help you see the importance of taking care and adding the minimum amount of titrant to the analyte being examined. Okay, now, again, we've talked about this with titrations before, but looking at this example up here, if I add just a little bit too much of the Mn2 plus even, then that can cause some big problems with my calculations because I will have added more of the MnO4 minus than I should have, and that's going to mess up our calculation for how much of the oxalic acid is there to begin with, okay? I think you guys can probably look that animation up yourself. Respond to the following questions prior to viewing the simulation. What physical and chemical changes, and how much should be needed. Okay, I'm going to let you guys work on that, and then tomorrow we'll probably check your answer to number 2 just to make sure that you're on the right track, because you need to know this number at some point while you're doing the titration. I don't know if you need to know it, but to develop a good procedure, you probably want to have a good idea of how much of that you need. Okay? So hopefully what we did in part 1 is enough of a catalyst for you that you're going to be able to figure out that second part after you look at the animation. And if you have questions on that, then we can talk about it in class. Okay. We'll see you in class tomorrow.